welcome everybody. We are here to this new continual learning seminar sessions hosted by ContinualAI as usual. And today we have the pleasure to host Lucas Caccia, which is going to talk about his recent work titled Reducing Representation Drift in Online Continual Learning. It's a very good paper, I think, with lots of also interesting authors and content there. I think we will talk about metric distance, maybe contrastive loss, and some other cool stuff that can be inserted into cross-entropy and stuff. So without further ado, I will let Lucas speak. So Lucas, please, the stage is all yours.
Great. Thank you for this wonderful introduction. I think it was the best one I've had so far, so thanks. So yeah, today I'll be talking about some of my work on continual learning, where we take a sort of a deep dive at what happens around task boundaries for replay-based methods. So this is joint work with Rafa Jendi, Nader, Tine, Joel, and Eugene. And yeah, let's get started. So the setting I'll be discussing today is the one of online continual learning. So what we mean by this is we kind of reduce it to class incremental learning, where you have a learner that sees a stream of data, and every once in a while, this stream of data, the distribution generating that stream is going to change. And once that happens, there's the introduction of new classes. And the goal here is to learn a classifier that can not only classify the new classes, but also remember how to classify the old classes. And here we're working in the shared head setting, which means that at test time, we're not going to tell the learner to which task a sample belongs to. And another important thing, which is not really getting as much attention in the setting, is that we care about anytime accuracy. So what I mean by this is it's important for the learner to be queryable at any given time during the learning process. So I'm sure everyone here knows why continual learning is not super easy, but just to do a small recap here and to give a bit of a historical perspective. So when we're doing continual learning, we're essentially violating this fundamental assumption about empirical risk minimization, which is that the data should be independently and identically distributed. But of course, if we're changing the distribution, this no longer holds. So here, the figure I'm showing here is from one of the seminal papers in CL from McCluskey and Cohen, where what you see here is that as soon as you start learning on the second task, we see that the accuracy for this first task really drops significantly, and that's what's commonly known as catastrophic forgetting. And another thing I like to point out about this figure is that there's actually a point where, like early on in the learning of the second task, where not only has the model forgotten how to perform on the first task, but it still hasn't learned anything useful for the second one. So essentially the model doesn't really know much at this point. So throughout the talk, we're really going to be focusing on why do we observe this catastrophic forgetting. Okay, so as I'm sure you're still aware of this, a very useful method in continual learning is to do replay. So just in a gist, experience replay, what it does is, so you keep a small buffer of previous data, and as you're learning these new classes or these new concepts, you're going to take samples from that buffer and rehearse on those past samples to make sure that you can still hopefully learn new stuff without forgetting the old stuff. And it's a really simple method, and to this day, I think it's one of the most effective ones. And it's a bit sometimes it's a bit frustrating as to how effective replay is, because like in my opinion, we're not really solving continual learning. We're just putting a band-aid on it and pretending the distribution hasn't changed. But it's the best one of the best tools we have. So this is we're going to be basing our analysis on experience replay. Okay, so coming back to a moment during the learning process, similar to the figure I was showing earlier, is just after you've learned the first task, when you start learning the second task, what happens to the previous task accuracy. And this is, with regular deep neural networks. We're not talking about 30-year-old neural networks as we were in the previous figure. Whoa. But we still notice the exact same thing, right? As soon as you start training on the second task, we see that the accuracy for the first task really drops significantly. And that's an issue, right? We like to avoid this. Another thing to notice here is that the model may or may not recover from this drop. And the reason it may or may not recover, it really depends on the buffer size. So if you have a big buffer, I guess the argument is that you have enough information inside that buffer so that you can correct this initial displacement so that you can recover the initial good accuracy on the first task. But if, as we see here, if the buffer is too small, then just accuracy stays low and the model doesn't get a chance to correct this drop in performance. Yeah, so as I said before, the focus of this talk is really to understand why we see this drop in performance. And so let me take you to the same moment in time, but now we're going to look at the representations of the model. So right now what I'm showing here is a t-SNE plot of the second to last layer of the model right before we start learning on the second task. So here the layer I'm talking about is just before we apply the final linear layer, which would give you the logits. It's just before this linear layer. So we have two classes, and we can see that the model does a pretty decent job at classifying those two classes. And those little triangles are the class prototypes. So the class prototypes are essentially just a row in your final linear layer that you can interpret as kind of the center of mass of that class. And it's really, in my opinion, it's really useful to look at the prototypes, because if you're doing cross entropy, if you're using cross entropy as a loss function, then all the interaction between points go through those prototypes. So looking at those prototypes gives you a lot of insight as to how the optimization process goes. Okay, so we finished the first task. We're going to start the second task. We have these prototypes. If we look at the gradient that's being sent back from points of the first task to the prototypes, you see something that's kind of expected, right? Just a small gradient that is pulling the prototype towards the center of mass of the points of that class. Now here's where it starts being a bit interesting. So if you look at where the points from the new classes land, what we see here is two things. First, even though we know that these points come from a different distribution, there's this really strong overlap in representations between the points of the old task and the points from the new task. And the second important thing is there doesn't seem to be any structure, at least yet, in the new points. At least right now, those new points are not really linearly separable. I can't really draw a line which would give me good classification accuracy. So these points are going to move. That's a given. So now let's look at what kind of signal are these points sending back to the prototypes of previous classes. And what we see is this. The gradient that's being sent back to the prototypes of class 1 and 2 is not only in kind of an arbitrary direction, but more importantly, it has a very large magnitude. And that's going to be an issue. And the reason that is because, well, first, these points, as I said before, they're not really learned, right? So the signal that they're sending back is pretty noisy. And the second thing is the movement, or what we call representation drift, that these prototypes are going to incur is going to be much, much larger because of this large gradient. So one thing to draw from this picture is really that the new points are going to send a strong signal back to the previous class prototypes. And as you'll see later on, that's going to be an issue. So another way to look at this phenomenon is to look at how much are the representations moving at every update. So here what we measure is during the learning process, every time we do an update or a SJP step, we forward the buffer before, like all the data in the buffer, we forward it before and after this update, and we look at how much these representations are moving. And what we see here is we see 4 spikes. And you probably guessed it, this is a 5-task stream. This is a split CFR10. And it just so happens that these large spikes really correspond with a task switch. So we know that at task switch, stuff moves a lot, and that might be an issue. Cool. So just to summarize where I'm at right now, hopefully what I've shown is that we have large disruptions in the representation at a task switch. And moreover, if you look at the accuracy of previous tasks, when you enter a new task, that accuracy drops significantly. So the hypothesis that we're making is that this abrupt change in representation is really the cause of this catastrophic forgetting. So by the way, if you have any questions, feel free to ask them at this point or any time to talk. I'll be happy to address those. Okay. Cool. So how do we handle this? So the approach that we take to tackle this is that instead of treating the incoming and rehearsal data similarly, we're going to do different stuff for each of those. So if you stop for a second and you think about it, there are some important differences between the incoming and the rehearsal data. So for the data that the model has just received, it's still being learned, right? So you would want these representations to be anything but static, right? You want that representations to move a lot and to adapt to the previous representations. Whereas for the rehearsal data, you kind of have something that's the opposite, right? If you go back to the t-SNE plot I showed before, the representations, there's definitely some value in keeping that representation because it does a good job at classifying the points from the first task. So you potentially want to move these representations less than representations from incoming data points. But if you look at your regular experience tree like pseudocode, which I'm showing on the right, what people tend to do is you take your new data, you take your old data, put it together, and just feed that to your model and hope for the best. So that's really the thing that we're going to be changing, hopefully to address representation drift. Okay, so as I said before, we're going to use different loss functions for the old and new data. So for the rehearsal loss, I just realized I switched my colors, but it doesn't matter. So for the rehearsal loss, we're going to use just a regular cross entropy. And it's really on the incoming loss that we're going to be focusing on figuring out ways to avoid this representation drift. And I'll come back later on as to why we're not modifying the rehearsal loss. But for now, just bear with me. We're going to be focusing on the incoming loss. So as I said before, the issue really here is that you have these large, this big gradient being sent back from the new task to the old prototypes. So what we want to do is we propose to learn the new task in isolation. So what we mean by this is we want to remove, we just want to remove the signal from the new task back to the old task. So the gradients that hopefully I've convinced you now that were kind of problematic, we're just going to remove those, say bye-bye, and then we're back to modifying the prototypes from the first class in a much more stable manner. Okay, so how do we do this? In the paper, we kind of propose 2 ways of doing so. So the first one that we propose is if you want to use the cross entropy loss, the way you do this is you simply just mask out, the logits that are not in the current task. So the code I'm showing to the right kind of does this. So what we do is, given incoming data, we actually sort of infer the labels in the current task just by looking at the labels in the current data. And then once you have those, you're essentially just going to mask everything but the classes that are present in your batch. And what this does it really just, as I said, just removes these gradients. Okay. And yeah, so that's it. So essentially our methods, we call them asymmetrical something because we're using an asymmetrical update rule. And the one with cross entropy is asymmetric cross entropy, or ERAs. Okay, so another way to do this, and I think this using metric losses. So the other way is you can use metric losses, and metric losses are really nice because so the way they work is you're given some points, some anchor points, and for each of those points, you're going to find one or several positive points and one or several negative points, and the goal is to bring the positives closer and the negatives away. And what's really nice about this approach is you have a much better control as to which samples are contrasted with each other. So if you want to avoid sending a gradient from the new task back to the old task, all you have to do is avoid comparing points from the new task with points from the old task. So just to get into details a bit, the main difference with just using a regular metric loss is when you fetch the negative points, because the positive points, just by construct in the setting that we're learning in, the positive points have to be within the same task. It's really when you fetch negative points that you have to be careful to only select negative points that belong to the same task. And if you do so, you're really explicitly avoiding taking old points and new points and sending a gradient back to the old points. Cool. So coming back to our previous figure where we're showing the movement at every iteration, if you compare to the left, if you compare regular experience replay with our version, which is careful about the gradient being sent back, well, we see that the bumps at task switch are much less severe. And similarly, if you compare the metric learning approach with the similar approach where there's no careful selection of negatives, you observe something very similar, which is that the representations in the buffer are much more stable. So that's hopefully that's something good. Okay, so coming back to our hypothesis, which was that if we handle representation drift, will this translate to a reducing catastrophic forgetting? Well, it kind of does, right? We don't see an initial dip in accuracy in the plot I was showing before, so that's really encouraging, right? So hopefully this will translate to better performance, but at least now we know that we're not severely disrupting our representations, which would then cause a drop in performance. Okay, so just to summarize once again, hopefully now I've convinced you that we've addressed the following issues, which was that we previously had large disruptions in the model's representation when there was a task switch, and that led to a significant drop in performance on previous tasks when you were starting a new task. So just to play devil's advocate here, you could just achieve these two things by simply freezing your model, right? If you're stopping the learning process, then everything is stable, and you're not gonna forget anything. So the real question now becomes, knowing that we're limiting the model's ability to move, is the model still able to learn new stuff? And yeah, you've guessed it, it actually works pretty well. So the model really is able to essentially just add new knowledge as it's seeing new tasks. And so these are results for split CFAR10. So the thing most people report is a final accuracy, which I'm showing in pink here. And if you compare it to other methods, we actually see some pretty significant gains in performance. And in this paper, we also decide to report the anytime accuracy. So the anytime accuracy is essentially just like a metric equivalent to the area under the curve for the anytime accuracy. And what we see here is like once again, we still have good performance on that. And it's a good metric to weed out methods that are anytime learners and methods that aren't anytime learners. For example, like GDOM, it gets really good accuracy. It gets really good final accuracy. But if you're in a setting where anytime performance is something that you care about, then you're probably better off with other methods, because other methods have the ability to start making predictions before the training process is over. Yes, so now that we have this, another question that I sort of had on the back of my mind was, does this still work if the task boundaries are not as hardly defined? So I guess the question now becomes, is the reason you observe drift because of hard task boundaries, or just because you're introducing new classes? So you actually did an experiment with blurry task boundaries where, in essence, you have tasks slowly morphing into one another. So new classes are gradually introduced in the stream, and old classes are gradually seen less and less until they're not part of the stream anymore. And even in this setting, we still see some pretty significant gains with respect to just when comparing to ER. And though that in this setting, you can only really compare to tasks-free methods. So there's a bunch of methods like SSIL, MIR, and iCarl that are simply just not applicable in this setting. Yes, so that's the gist of the results. One last thing I'd like to mention is actually two things, if the time is good. So Andrea, feel free to cut me off at some point if I'm taking too much time, but I'm just going to assume that I have a few minutes left. So yeah, the first thing I'd like to mention is that, so in our analysis, we've given each method the opportunity to leverage data augmentations. And for CFAR10, what we notice is that using augmentations is essentially a tide that lifts all boats. So comparing methods that do leverage it with methods that don't really gives an unfair advantage to the methods that do use augmentations. For example, if you look at ER, the accuracy for m equals 100 in our larger buffer sizes, you go from something that's definitely subpar compared to other methods to something that's very competitive and actually outperforms methods like iCarl and MIR and SSIL when it's given the ability to leverage augmentations. So yeah, augmentations, all methods deserve it. Feel free to propagate that to all your baselines in your paper. The second thing I'd like to talk about is, in this paper, we decided to monitor the training flops that's required to train a method. Because as I'm sure you're aware, if you're giving infinite memory and compute, you can just solve forgetting by just constantly retraining on all the data you've seen so far. So it's really important, especially in the online setting, to monitor compute, because in most scenarios where you're deploying models online, you probably want to make sure that your model is that the approach that you're going to be deploying can still work in constrained settings. So what we see here is there are a few methods that are much more heavy on training flops. For example, dir and especially MIR. Especially for MIR, the step where you fetch the points, actually forwarding points to calculate which ones are the most maximally interfered. There's a cost to this, and that should definitely be accounted for. So for what it's worth, we also explored methods. So now that you know this, it's good to go back to these methods and see if there's ways to make it more efficient. But yeah, I guess all in all, it's good to look at compute. And the second point about compute is methods that use nearest class mean classifiers like iCarl. In the online setting, there's a big cost associated to this, because so the way NCM classifiers work is when it's time to do predictions, you don't have a linear classifier on top of your features. What you're going to do is you're going to forward the whole buffer and average representations with respect to their classes. So you end up with class representatives. And when it's time to make a prediction, you just find the class representative, which is the closest to your input point. But the problem with this approach in the online setting is, since you're constantly updating your model, you constantly need to re-forward your buffer to make this prediction. And there's there's definitely a cost to this, and that's more noticeable in larger buffer sizes. For example, here I'm showing results for split CFAR 10, split CFAR 100 on the left, and many emission on the right. And since the buffer are bigger here, if you look at the flops for ICAR, they're definitely, I think, like an order of magnitude more than other methods, which can be concerning. So yeah, that's pretty much it for the results. We observed something pretty similar for these data sets, not quite as pronounced as split CFAR 10, but still the methods we propose are either performing the best or on par with the best while having the least compute and memory budget. Okay, I will stop here. So I guess I had a few final remarks, which is that the structure of the optimization problem matters, right? As we saw here, like classifiers tend to forget a lot, which I think is really due to this representation drift. And I think that identifying this issue kind of explains why methods like generative modeling and self-supervised objectives tend to forget a lot less, right? If you think about a reconstruction objective, there's nothing really being pushed down, or when there's a new task, the per pixel difference or loss is definitely going to change much less than the classifying objective. So just something to keep in mind, and I thought I'd give a bit of perspective. So yeah, thanks for listening. If you have any questions, feel free to ask them now. And thanks to the organizers for letting me talk about my work.
Thank you very much, Lucas, for your presentation. I think it's very stacked with insights and also connections with existing works, and it really will be useful for future explorations. So before opening the discussion, I just wanted to ask one question, one or more, depending on the time we have. But so basically, I think that this work is mainly related to study the behavior of the output layer. Right? So are we talking about a pre-trained network with an output layer on top on which the method is applied, or is the network fully trained from scratch?
So here we did, the networks are initialized from scratch. If you were to retrain the network and fix the representation, only fine-tune the last layer, that would definitely be much less prone to representation drift, because you're basically you're fixing the representations. But it still becomes interesting to see. That's a good question. I think if you were to fix everything but the last layer, you'd be okay. If you were to fix, say, the trunk of the model, but leave, say, 2 or 3 layers on top, you might still be experiencing some similar issues. But if you leave everything but the last layer, you should be able to mitigate this representation drift.
Yeah, thank you. Can you please stop the screen shares so that I think we can optimize the live stream? Great, thank you. So have you tried any experiments also with CWR? Let me remind the full name, the copy weight with RayInit, which I think has interesting connections with your work, because in CWR the behavior is similar, not the same because there is not replay involved there, but they also considers only the current classes in the mini batch and zero out all the other weights, just to remove the interference, or at least limit the interference. So I was wondering if you did some experiments with CWR, which I think may require a pre-trained network, but not in not all the cases. So I just was wondering about this.
Yeah, that's a good question. Actually, so we actually did some in the paper. We compare against method called SSIL,
Mm-hmm.
which stands for Separated Softmax for Incremental Learning. And so it kind of does something similar where, from what I understand, the method you're talking about isolates, uh, has this isolation between old and new stuff. And the SSIL method is actually very similar to our method. The only difference is they also isolate the rehearsal step. And what we see when you do this is that isolating both the incoming loss and the rehearsal loss means that there's no point in time where the model is comparing points from the current task and points from the old task. And what that results in is that the model basically is unable to do inter-task classifications. What it does is the new points will always predict that they belong to the old classes. I'm not exactly sure if this answers your question, but
Yeah, more or less it does. Yeah, so thank you. I was also very pleased to see the blurry task boundary setting, which I think is moves beyond a bit class incremental, right? So like in the new incremental and classes scenario, in which you transition from one task to the other in a slightly blurred way, in fact. So it's also more realistic, right? Than shifting altogether in one instant all the classes at once.
absolutely. And I think it's actually a bit easier. Like the setting, like the added restriction of having hard task boundaries, I'm not really sure if it brings anything to the table besides just making the problem harder. But like just playing more and more in the online setting, I think that there's a few things that we could probably be more relaxed about. Like I've seen a few papers giving more training time to methods that work on harder data sets. And I think that's definitely, the more I play with these data sets, I think that's something that we should probably try to shift the community towards, because it's hard to disentangle the online learning aspect versus the catastrophic forgetting aspect.
Yes, exactly. So, are there any questions from the audience, from the other people? Feel free to unmute yourself or write in the chat. I'll monitor it.
I have one.
Yes, please, Antonio.
So, what do you think would happen if you switch the cross entropy error with mean squared error? Because if you use mean squared error, then you have that all the units are independent. You don't have the problems that you have with the cross entropy. And you can decide, for example, to mask the units, but maybe you don't need it.
Interesting question. So I guess if you were to use mean squared error for classification, what exactly would be the target for each output? Okay, I guess the mean squared error between the class prototype, the correct class prototype, and the output. I guess that would kind of do a similar objective where you would be avoiding a negative gradient back to the previous task. It would also have the disadvantage of keeping every class independent. Like if you do mean squared error for classification, you could technically always predict the zero vector for all classes and learn the prototype for each class to be the zero vector, and you get zero error. But I think it's good to think about stuff like this. I'm not exactly sure what would happen, but I think it might be a little hard to use MSE for classification.
Yeah, just a simple way to remove this problem of the dependence between the units.
Yeah, but that's a good point. Like I think the Arcol paper does something similar where they use a sigmoid for each class, so there's no direct dependence between the classes. I've played a bit with this. It just made stuff kind of worse, but it might just have been the case that I wasn't like in the right hyperparameter space to make it work. But that's that's definitely an interesting direction. In general, I think that taking some time to think about the objective that we're trying to optimize, especially for continual learning, can have a really significant impact on performance.
Yeah. I mean, my point is that the cross entropy is maybe the worst choice that you can make for continual learning. The mean square error maybe is a stupid choice for classification, but at least it doesn't result in catastrophic forgetting as you get with cross entropy.
Yeah, no, I agree with this. I think that I'm very curious to if someone could point me to an example of catastrophic forgetting that's not directly linked to classification. Like I believe in forgetting. If the distribution changes, if you train a lot on the new distribution, you're definitely going to be shifting away from what you've seen previously. But like, I think the focus was so much on catastrophic forgetting and continual learning that it's unclear to me if the methods we're designing for something else than classification will really translate to gains in like more realistic setting where you might not want to do classification. But yeah, that's a good question. I don't have a good answer to that.
Yeah, thanks.
I also have a question. Do you think that this representational drift could be worsened in the case of single head setup? Because I assume in a single head the classes from different tasks need to be somehow aligned so that the linear classifier on top tries to separate them. So if there is a distribution shift, it kind of affects all the previous tasks. But in the case of multi-head setup, the penultimate representation layer can actually be more disentangled, and it may not affect all of the previous tasks with the same amount. So, what do you think about that?
Yeah, that's a good point. I think that in the multi-head setup, since all the heads are independent, you're sort of by design not sending gradients from one task to another. So I'm fairly confident that, as you've pointed out, in a multi-head setup, that phenomenon, if you were to see it, would be much, much less severe.
Okay, are there any other questions? Okay, if not, let's thank Lucas for the presentation and for the questions, to all the answers you received. Thank you very much, Lucas.
And likewise for hosting me. Sorry, didn't mean to cut you off.
No, don't worry. So thank you everybody for staying with us for this short amount of time. Remember that this is a live streamed talk. You can find it on YouTube if you are here, or if you are already on YouTube, you can subscribe to the channel of ContinualAI. So thank you very much everybody, and I'll see you soon in the next ContinualAI seminar. Bye!